Here's a few symbols and things that we should take into consideration when we are writing a balanced chemical equation. To make our equation as detailed as possible, you might see these phase symbols written behind your reactants and products. It's a good thing. It's just telling us the phases that we would expect in our chemical reaction. Now obviously things like an S or solid, often that would be maybe a metal, or it could be a precipitate on the product side. L is liquid, G is gas, that's an easy one. And then the AQ, aqueous, we mentioned earlier. The two that get mixed up a little bit are the liquid and the aqueous. Because when you're in the lab, they both look the same. Like aqueous means dissolved in water. Dissolved in water. It's a solution. It looks like a liquid. And so then sometimes people are like, well, what's the difference? When do I use the L liquid and when do I use the aqueous? Well, of these four, the L liquid is probably the one that's used the least. Liquid is only for something that is a pure liquid. Like it exists in the liquid phase as it naturally occurs. Things like water could be listed as a liquid. Things like alcohol, hydrogen peroxide. If it occurs in nature in its pure form as a liquid, we would use the L. But aqueous is not something that's pure. This is something that's been mixed with water, dissolved in the water. And so, for example, like we could have sodium chloride as a solid. So if you saw solid sodium chloride in a chemical reaction, you would know that it's just the white, crusty solid. You could see NaClAq, and then we know that it's a solution of sodium chloride. It's not a pure substance. It's sodium chloride solid that's been mixed and dissolved in water. But you would never see this. This would be a big fat sad face. These are happy faces. Sodium chloride does not exist as a liquid. Like in its pure form, it's never going to be a liquid. I mean, I shouldn't say never, but its melting point is like thousands of degrees. Like rarely would it ever be a liquid. And so there is a difference between the L liquid and the AQ aqueous. Aqueous would mean that something is dissolved in water. L, it naturally occurs as a pure liquid. Sodium chloride does not naturally occur as a pure liquid. We would not use the L for a sodium chloride solution. And the other thing that maybe we should mention before we really get into different kinds of reactions is that there are some elements that in an equation may exist diatomic, meaning they come in pairs. Two atoms of the same element bonded together. They kind of form a pattern on your periodic table. It's hydrogen, and then it starts off with nitrogen, oxygen, and all down the halogens. Now, most of them are gases. Hydrogen, nitrogen, oxygen, fluorine, chlorine. Most are gases. I just kind of remember that like almost 7 of them. I guess this periodic table's got tennessine on it. 1, 2, 3, 4, 5, 6, 7, 8 of them kind of make like this, I don't know, like number 7 over on the side, starting with nitrogen over to fluorine and all the way down. And then baby hydrogen up in the corner. So a lot of them are gases. Over in that non-metal block, it would start with the gas nitrogen and then down through all the halogens. So if I were writing a balanced equation and they said something reacts with oxygen gas, well, as an element, I would write my equation with oxygen gas being diatomic. If I were writing something like chlorine gas reacts with something, if it's the element chlorine, it would exist as Cl2. So when they're in their elemental states, meaning not bonded to anything, these elements come in pairs. And when we do the bonding unit, we'll kind of see why. that they're often much more stable with a partner than they are on their own. Now, when I write a formula, chlorine is not diatomic. Like, obviously, we don't write NaCl2, like, oh, it's diatomic. No! Sad face. Only when it's in its elemental form. So if I saw something like chlorine gas reacts with something, well, chlorine gas is diatomic. If chlorine is in a compound, then I write the formula dependent on the charges of the ions in that compound.